Welcome back to the Simpkins Physics Corner. It's your host, Mr. Simpkins, here, academic physics for some free falling. We're talking about free fall today. Last week, we finished up acceleration with a little quiz. This week, we're going to say, well, how does acceleration, what we already know, inform us about things that fall? Of course, if I hold something up, it's not accelerating. If I let go of it, the force of gravity takes over, and we experience uniform acceleration from that point. So here it is. Force of gravity causes the acceleration down. Now we know to accelerate is to change velocity. To accelerate is to change your velocity over time. And so if we are accelerating, our velocity is changing. Now this unit of meters per second squared is kind of a funky thing, right? We're like, well, what is a meters per second squared? We're going to talk about that today. We're going to talk about when things fall, what happens to the distance that it falls every second, and what happens to the speed that it travels as every second passes by in free fall. So let's get into free fall for today with our notes. So I want you guys to grab the notes that are posted here in the Week 10 launch. You can follow along as we talk about free fall today. So if we look at this little graphic here, this is a very informative one. It's showing us a ball falling. And you notice the guy drops it from up here. And you notice that the ball, as it falls, it seems to be covering a greater and greater and greater distance. Well, it's because it is, but let's talk about why that is. Let's track the speed. Now when we say acceleration due to gravity is 9.8 meters per second squared, we're going to round that to 10 for today, just to talk about the ideas. So you may be a little bit, uncomfortable with our imprecision, but it's going to be useful for our conceptual understanding. So as we look at how fast we go, if I hold something, it's at rest, and I drop it. Now let's talk about what 10 meters per second squared means. That means 10 meters per second per second. Well, what's that mean? Well, that means that every second that goes by, your speed changes by 10 meters per second. Every second. So if your speed initially is 0, after 1 second, your speed would change by 10. Your speed would be negative 10 meters per second. Why negative? Because we're falling down. What about after another second? Well, how much does the speed change every second? By 10 meters per second. Every second. So then your speed would be negative 20 meters per second. I should say velocity would be negative 20 because speed doesn't have direction, right? How fast are we going after 3 seconds? 1 second goes by, our speed changes by 10 meters per second every second. So we'd be going negative 30. And if you start to seeing a pattern, that's because there is one. Here, 40 meters per second, negative 50 meters per second. And now you see why we round to 10, because the math with 9.8 on this would be really ugly and get out of the way of our understanding. When you say that something accelerates with a rate of negative 10 meters per second squared, that means that every second that goes by, your speed is going to change by an amount of 10 meters per second every second. So look at how the definition of our acceleration informs how much our speed changes every second. And this is where we get this expression, which you'll find on your equation sheet. Now, it only works when you're at free fall and you drop something from rest, but we see that pretty often, so it's a useful equation. V equals gt. What does that mean? That means the velocity you're currently traveling can be calculated by taking 10, or 9.8 in some stances, and multiplying it by how long you've been falling. Like, see how it would work at 4 seconds. The velocity would be equal to negative 10 meters per second squared times 4 seconds. And if we did the math, we'd get negative 40 meters per second. So when we are doing physics and science, we look for patterns, and sometimes those patterns will allow us to develop equations. So in this case, the equation for how fast you're falling after a certain amount of time is V equals gt. So if you look at this little graphic, you can fill it out on your notes. I believe it may be already. But you see how after 1 second the speed's 10, then I draw a little speedometer arrow to 20, then we'd be going 30, then we'd be going 40, then we'd be going 50, going 60. So that's what would happen with your speed, because we're accelerating at a rate of 10 meters per second squared, or 10 meters per second every second. That means that our acceleration there is changing our speed by 10 every second that goes by. What about how far you fall? Well, think about this. If you're falling faster every second, won't you also cover more distance every second? And if you look at the picture, you see that quite nicely. The picture shows a small spacing, and then a larger one, and then a larger one, and then a large one, and it continues on like that. So we see that when you accelerate, you cover a small amount of distance at first, and then you cover a greater and greater and greater amount of distance as you continue to fall faster and faster. Now, this comes from this equation, which is on our equation sheet, all right, and it's under the Chapter 3 equations. But if we take this equation and we consider when you drop something, think about this. If you drop it from rest, what's your initial speed? It's 0, and 0 times time is 0. And we also say that if we drop something, if a problem doesn't tell us, hey, you need to specifically begin your problem at such and such a location, we can set the initial location equal to 0. And so what that means is the distance that we fall, this distance x, is going to be determined by 1/2 the rate of acceleration times time squared, because of the way all these things relate to each other. And if we do that for vertically, because we're falling, in math class, this is the x-axis, of course, and this is the y-axis. So all of our equations with x for distance, we can use y for distance this way. And if we do that, the distance that you fall when dropped from rest in a free fall scenario is y equals 1/2 at squared. All right, so let's try this out. How far has the ball fallen after 2 seconds? After 2 seconds, let's see. Y equals 1/2 negative, we're going to use 10 meters per second squared, times 2 seconds, and that's going to be 1/2 times negative 10 times 2 squared, which is going to be 1/2 times negative 10 times 4. That's going to be half of 40, or negative 20 meters. Now, why negative is because we're falling down, right? Down is usually negative. But what that means is that after 2 seconds, we will have covered 0 to 0 meters, or 20 meters. So after 5 seconds, or sorry, after 1 second, you cover 5 meters. That's not that much, right? But then in another second, you cover another 15, so you're all the way up to 20 meters, right? So you can see that you're going to be gaining speed. You're going to be increasing the distance that you travel every second. So what I want you guys to do is try this out for the rest of them. You'll start to notice a pattern, by the way, but I'd like you to try it for here. So here you do y equals 1/2 times 10 times 3 squared, right, for 3 seconds. That's how far you fall after 3 seconds. Y equals 1/2 10 times 4 squared after 4 seconds, and so on. You can go down and calculate how far you fall after each second. Well, things don't always just drop off of cliffs. What if we send something up into the air? What if we launch something up into the air? But when we do drop things off of cliffs, we'll get to that in just a second. When we do drop things off of cliffs, you'll look at your equation sheet. You'll see these 3 special equations. Now, they're special because they're kind of cheat equations, and they're cheat equations because they're all derived specifically only for things that fall from rest. And it says that on your equation sheet. It says free fall. So you don't overuse these equations. Only use them when you have a free fall scenario. So V equals GT gets you how fast you're falling at a certain time after falling in free fall for T. Y gets you how far you've fallen. And then if you look at this equation, I solved it for you for T. That would be how long it takes to fall a certain distance. Now let's talk about tossing things up into the air. We know that what goes up must come back down, right? Of course. But that's because of the acceleration that we're constantly undergoing. We're always, as we toss up in the air, we're going to be accelerating at a rate of 10 meters per second squared down, which means our speed is always going to be changing by 10 meters per second in the downward direction. So on the way up, of course, your speed is decreasing. All right, so it looks like this. So if you throw it up here with a speed of 30, after 1 second, it's going 20. After another second, it's going 10. 10 minus 10 is 0. 0 minus 10 is negative 10, 20, negative 30, negative 40. So it's going to go up, and every second that goes by, it's going to change by 10 meters per second, every second that happens. What is the velocity at the instant the ball reaches its highest point? Well, take a look. Here it is. All the way at the top, we're going from positive velocity, stop, to negative velocity. Then if you do that, at some point, your velocity has to be 0. All right, so at the very top, you stop for a second. The ball goes up, stops, comes back down. On the way down, the speed is increasing. Why? Because you have a downward velocity, and you also have a downward acceleration. And when velocity and acceleration are in the same direction, that means a gain in speed. So you'd be increasing your speed. When we say how much does the ball change its speed every second, we would say the speed changes by 10 meters per second every second. Why is that? That's because g, the acceleration due to gravity, is 10 meters per second squared, and it's negative because it's down. So let's go ahead and plot what we see in that picture on a VT graph. We're doing VT graphs. At the beginning, our velocity is 30, so I'm going to plot that as 1 second or 0 seconds. After 1 second, it's 20. After another second, it's 10. After another second, it's here. So let me pause for a second. So far, we're at 3 seconds. Velocity is 0. That's how I'm going from the picture to the graph. After 4 seconds, we're at negative 10. 5 seconds, we're at negative 20. 6 seconds, we're at negative 30. 7 seconds, we're at negative 40. Now, if you notice, it's a little bit choppy, but if I were to fit this, if I were to fit this, it would be a nice straight line, as straight as I can draw it. If I could have a straight line on there, it would be very, very straight. What do you think the slope of that line would be? Well, we notice the slope of the velocity graph is negative. So we know it's negative something. And the slope of a VT graph, rise over run, would be change in velocity over time. Well, how much does our velocity change every second? By 10 every 1 second. So our slope here is negative 10. Oh, right. The rise over run of a VT graph gets us acceleration. So if you take this VT graph, and you notice it's a nice straight line, or as straight as I can draw a straight line with a stylus, this straight line would have a slope of negative 10 because that's the acceleration due to gravity. So this is what the VT graph would look like for something that is tossed up into the air. It would start with a large positive velocity. It would take a stop at the top, and it would come back down with an increasingly negative velocity. So the slope would be negative 10 meters per second, or squared, or meters per second squared. If you took the slope of that graph, what do you think the magnitude would be? Okay, so the magnitude would be 10 meters per second squared. Sorry, this should have said the acceleration. We talked about that at the top, but the slope gets you the acceleration. Okay, so that's a quick little overview. I want you guys to watch this video, take the notes along with us. And as we continue on for the rest of this week, you're going to take a look at your equation sheet, which has these equations on it. And you'll see that when I check in with you tomorrow, if you're here, you're going to be doing a tennis ball lab. And if you're at home, you're going to be looking at some of these free fall problems and how these equations work out when we use them. Until next time, I'm Mr. Simpkins with Free Fall in Simpkins Physics Corner.